So let's do this again. When last we spoke, we had left off at the beginning of this section, section 4.5. And we know that if y is equal to the ln of x, then e raised to the y is equal to x, right? Now, we're going to go ahead and take the derivative of both sides here. d dx of e to the y is equal to d dx of x. And this is going to evaluate out to be e to the y dy dx is equal to 1, right? Now let's divide both sides by e to the y so that we can isolate this dy dx. dy dx is equal to 1 over e to the y well, to start off with, we had said that y is equal to the ln of x. So e to the y is going to be equal to 1 over e to the ln of x. But e to the ln of x, that's just equal to 1 over x, right? So what we found here is that the derivative of the ln of x is equal to 1 over x. And more generally, if we have e raised to some function of x, my mistake, the ln of some function of x is what I meant to say. This is going to evaluate out to be 1 over that function of x all times the derivative of that function of x. And this is just from an application of the chain rule, right? We now know, generally speaking, or rather specifically speaking, the derivative of the natural log is 1 over x. So that general case, using the chain rule, is going to be 1 over the function of x times the derivative of that function of x, right? Make sense what I mean? So looking at these rules side by side, the derivative of the ln of x is 1 over x. The derivative of the ln of some function of x is 1 over that function of x times the derivative of that function of x. This is actually really super convenient. So it lets us solve a bunch of problems that we otherwise wouldn't be able to. But let's consider for right now a simple example. Let's consider the ln of 2x. We can think of this as f of x equal to the ln of u of x, where u of x is equal to 2x, right? So the derivative of the ln of u of x is going to be equal to 1 over u of x times the derivative of u of x or we can just write it as 1 over 2x times 2, or just 1 over x. Yep. Now really quickly comparing, they went through the same process, right? They declared that their interior function u of x is going to be equal to 2x. They just applied chain rule and the derivative of the natural log. Now, let's consider one of these examples. What's a good one for us to look at? What do y'all think? Pick one. C. Okay. Yeah, let's look at C. So in C, we're saying that our function is equal to the ln of x over x. Well, here we're going to have to apply the quotient rule, right? So applying the derivative we're going to get that this comes out to be x times the derivative of ln of x minus the ln of x times the derivative of 1 over x, all of this raised, or all of this over x squared. Just applying the quotient rule here, right? Well, this thing is going to reduce after we go ahead and evaluate these derivatives in the numerator. We're going to get x times 1 over x minus the ln of x times 1 over x squared all over x squared. My mistake, I miswrote this up top. This is supposed to be the derivative of x. I apologize about that. There we go. Now that looks right. Just looking at it like, no, this is not right. What am I doing wrong? Well, these x's in this left term, they're going to cancel, aren't they? They're going to reduce to just 1. So what we're going to be left with then is going to be 1 minus the ln of x over x squared. And comparing our solution to theirs, applying the quotient rule, evaluating those derivatives, and then simplifying. It comes out to the same, right? Now looking at another problem, here we've got the ln of the square root of the quantity x plus 1. At first sight, this looks like it would suck to evaluate, doesn't it? But if we go ahead and apply those properties of the logarithm, we can pull the square root out as a coefficient, right? Making this a lot easier to evaluate. So applying the derivative onto 1/2 the ln of x plus 1, we're going to get 1/2 times 1 over x plus 1. Make sense? All right, I'm going to give y'all, say 2 minutes to work on this one. See what you come up with. This is ugly, isn't it? This sucks. Just out of curiosity, how many of y'all try to rewrite this as the ln of x to the 5th plus 2x cubed plus x? Anybody?
I wrote it like 5x plus x squared.
The interior?
I fucked that up.
Yeah. One thing we could do is just go ahead and evaluate what's inside, right? Squaring x squared plus 1 is going to give us x to the 4th plus 2x plus 1 multiplying all of that by x, we're going to get x to the fifth plus, my mistake, I forgot a square there, 2x cubed plus x. So we could evaluate it like this. But even that looks ugly, right? So why don't we not go that route? Why don't we instead use the properties of the logarithm to make this easier for ourselves? Using the properties of the logarithm, we can rewrite our function as the ln of x plus the ln of the quantity x squared plus 1, that whole thing squared, now we've got a property for a logarithm that we can apply here to get this 2 outside, right? So let's go ahead and apply that to get the ln of x plus 2 ln of x squared plus 1. That looks a whole hell of a lot better, doesn't it? Let's apply the derivative to this one now. So, d dx of the ln, I'm going to write all of this all over again, x squared plus 1 of that quantity squared. This thing is equal to d dx, the ln of x, plus d dx 2 times the ln of x squared plus 1. Yeah, this is going to be a lot easier to calculate, isn't it? Well, because we're multiplying by a constant here, we can just go ahead and pull that 2 out, can't we? So when we evaluate this, we're going to get 1 over x plus 2 times the derivative of the ln of x squared plus 1, which is going to be 1 over x plus 2 times 1 over x squared plus 1 times the derivative x squared plus 1 so in the end, this all comes out to be 1 over x plus 4x over x squared plus 1. Now in this last move, I just went ahead and simplified as I calculated that last derivative, right? It said this thing comes out to be 2x times this 2 gives us 4x up here. And we're going to keep x squared down below, right? So knowing these properties of the logarithm can save us some headache and some heartache. Because let's imagine we wanted to actually calculate this straight out.
You couldn't.
We could, it just takes some more time.
I didn't think you could cross multiply with the exponents with the Oh, yeah, never mind, because it's an X.
Well, let's look at it really quick. This thing we just said was the ln of x to the fifth plus 2x cubed plus x. Applying the derivative. Wait. This will evaluate out to be 5x to the fourth plus 6x squared plus 1 all over x to the fifth plus 2x cubed plus x. They don't quite look the same, do they? Well, after some simplification, we find that they are. First thing we can do is factor out an x here and start rearranging some of our terms, and they simplify to the same thing in the end. Is everybody cool with this? Yep, cool. Having said that, notice in both cases, I never actually calculated the derivative straight onto this. I did some simplifying first, just because if we're going to apply the derivative straight onto this, sure, we get this in the numerator, in the denominator, but then we're going to have to apply the product rule, the power rule, and the chain rule to this. So no matter what, simplify always. But when you can apply those derivative rule, I mean those logarithm properties, to get it a little bit further if you can. It'll just make the work that much easier for yourself. Oh, I was going to compare two. Really quickly, just looking at our solution on the far end comes out to be the same thing. And like I said, I'm not going to try to work out that derivative on the far left and try to simplify it. If you all want, you can, but it should come out to be the same. So, never mind the typo mistake down here at the bottom. It's supposed to be a 2 in the numerator, or in the denominator. We want to know some details about this function. Particularly, we want to know what this graph is going to look like. So what this thing's supposed to be is x squared over 2 minus the ln of x. So if we're going to analyze the graph of a function, we're going to take the derivative, right? So let's go ahead and do that. It's going to come out to be x minus 1 over x. Agreed? The derivative of x squared over 2 is going to be 2x over 2, so those 2's are going to cancel. The derivative of the ln of x is 1 over x. We're subtracting it. We're going to get that subtraction here. Now from here, we would want to find like critical numbers and everything else. So let's go ahead and do that. Setting that equal to 0. we get x minus 1 over x is equal to 0. I don't like this already. Let's add x, or 1 over x to both sides. Now let's multiply both sides by x. Then we know x is going to be equal to plus or minus 1. Do we need to check both of these values? Well, first, what did we just find? Possible critical numbers, right? So what do the critical numbers tell us? Tell us when we have a flat spot in our function, right? Tells us when the slope is 0. So it's going to be something that looks like this, like this, like this, or a few other possible combinations of these things, right? But notice here, we have a negative 1, right? We can't put in a negative into the ln of x. So because we can't put in a negative here, we keep only the positive 1 value. Now let's think about this some more. Why is that? Why is it we can't put a negative in here? Because the domain of the ln of x is only from 0 to infinity, right? So since negative 1's not in there, we can go ahead and throw it out. Make sense what I mean? The reason why I wanted to show this problem is to make this point, that the domain of the ln of x isn't all real numbers, so we can oftentimes simplify what we have to work with a little bit. We can make inferences about our data or about the results on our work to conclude some things moving forward. Everybody cool with this? So jumping to the next slide and looking at everything, we did the same thing. We said, let's just go ahead and find the critical numbers, take the derivative, set it equal to 0, evaluate it down, and you get x is equal to plus or minus 1 as possible critical numbers. But negative 1 isn't in the domain of our function, so we can throw it out. We could go on to actually evaluate like the second derivative and so forth and so on, and find out what this graph is really going to look like. But for right now, this will do. So having said that, let's consider this problem here. In this problem, what we've got is an experiment that was ran over 200 students over a period of 4 years, where data was taken every 6 months. After the experiment was ran, they found a model to fit the data. There's a few things we need to know about this model first and foremost, before we do anything else. One, notice that here, time is in months, right? We said the experiment was taken over 4 years, and here we're restricting time to be between 0 and 48. So it has to be in months, right? Also notice the data points are taken over 6 months, every 6 months. So when we look at the model versus the data points will cluster around these interval values, right? These every 6 month periods. What we're looking for is going to be the slope, the rate of change at 12 months. So going back to the original problem, we're asked to find what the rate of change is after a year. So the function is equal to 91.6 minus 15.6 times the ln t plus 1. T is restricted to 0 to 48. Here, let me replace that variable with t. Now we're going to take the derivative of this. The derivative of this is going to go to 0. We've got this constant outside, so we can ignore it, just hold it in its spot right now. The derivative of this is just going to be 1 over t plus 1, right? We've just found the derivative of our function. This thing is equal to the rate of change, right? dp dt. Now we're going to plug in a year. But again, time is measured in months, so a year is going to be 12. Throwing in 12 here. This is going to come out to be 15.6 over, or times 1 over 13. I'm not going to pretend to know what that actually comes out to be. I know it's 1 point something, but that's it. So let's jump to the answer really quick. It says this thing evaluates out to be negative 1.2. Now some more points on this data. When they go to report this data represents percentage scores, right? So they can't report negative 1.2. They have to say that the rate of change is decreasing by 1.2% per month. Does that make sense? So just some details on how to report this data. We can't report that negative. We have to turn this into a decimal. So just remove that negative, tack on the percentage sign, and then say the data was decreasing. Make sense? Now I want to make this point just because no matter what you do, at some point in time, you're going to have to report data back. And it's going to be important that you know how to actually report the data and to interpret it. As an example, you're going to have to do this. My little sister's in the Navy and just recently had to ask what the standard deviation function was because she had to report some data. Unfortunately, she got to mom and not to me. I think she figured it out, but nonetheless, I just think it's important that we also know how to report some of this data too, and to interpret the information. So far up to this point, this whole time we've been talking about just one base, right? We've been talking about e to the x and ln of x. But when we started, I had said that we could generalize this to b to the x, the log base b of x, right? And what these things are doing, let me rewrite this a little bit. What these things are doing are undoing each other, right? The logarithm says, given some base b, if I know b raised to a power evaluates out to be x, then log base b of x is going to tell me what that power has to be, right? Agreed? So just as a more general form of what the logarithm is, this should give us some idea, right? We said that the ln, well, this is a special case when our base is e. So there's really no difference between the ln and the log, except for what our base is. Agreed? Now let's consider I gave you this, log base 2 of 8. I asked you to evaluate that. What would that come out to be? 3. This is 3. Why is this 3? Well, go ahead. Yeah, exactly. So what this is asking is for us to solve this, right? We're saying base 2 raised to some power is equal to 8. Well, here, this is going to come out to be 2 to the third, 2 to the third is equal to 8, right? So we know log base 2 of 8 is 3. Makes sense? Let's look at a little bit more of this. This is a pretty classic example because this is an easy one to point to make this comparison. But let's consider log base 3 of 81. Log base 3 of 81 is equal to y, right? What this tells us is that 3 to the y is going to be equal to 81. Well, I have no clue what this y is going to have to be. But I do know that 81 is 9 times 9, right? And I can rewrite 9 as 3 squared. So because we share a base here, we can use those properties of exponents say, hey, this thing comes out to be 3 to the 4th, right? So y up here must be 4. And check it out. That's exactly what we got. So all logarithm's asking you to do is say, given a base, we want to find out what power it's going to take to get 8, or to get whatever we put through the logarithm, right? So we can think of it in a sort of reverse process. So we can move this direction or the other direction, right? So effectively, they're just undoing each other. Does this make sense? So if we have a function, f of x is equal to b to the x, this thing is y, the inverse function is going to be log base b of x which tells us that f of x, well, let me rewrite it as f of the inverse function of x is equal to b log base b of x. Well, log base b of x evaluates out to be whatever power you need to take b to in order to get x. So we're just going to get x back, right? Similarly, f inverse of f of x is going to be log base b of b of x well, log base b of whatever we're taking it of is asking what power you need to raise b to in order to get this thing, right? But here we're told b of b to the x, so it's got to be just x. So logarithms and exponentials undo each other, is what I'm saying. They are inverse functions of each other, assuming you hold the base the same. Does this make sense to everybody? Folks at home, does this make sense?
I'm with it.
With it? Awesome. All right. So having said that, what if, actually, who's got a calculator with them right now? Anybody? Nobody? Okay. I'm going to take out mine really quick. Yeah, it doesn't. All right. It doesn't have a general base, right? It's just log and ln. So I want to make this point really quick about calculators. Only have 2 different logs in general. I'm going to write that out here on the board. Your typical calculator only has log and ln. Well, this is log base e of x, and this is log base 10 of x. But what if you want to calculate log 2 of, say, e to the 3rd? What this is asking is what power you need to raise 2 to get e to the third. Your calculator can't answer this question because it only has log base 10 or log base e. It doesn't have log base 2. So we need a way of working around that. To work around that, we have a formula called the change of base formula. And what the change of base does, this is a specific version of it. What it does is it lets us evaluate one logarithm in terms of another logarithm. Since we have the ln on our calculators, why don't we try to evaluate our log base 2 of e to the third in terms of the natural log. Using this change of base formula, this thing can be rewritten as the ln of e to the third over the ln of 2. We've got our base here, right? And we've got our x here, we're passing through. Make sense? Well, this thing is going to evaluate out to be 3 over the ln of 2. And without a calculator, I don't know what the ln of 2 is. I know it's going to be a decimal value, probably close to 0.9, but beyond that, I don't know. We're going to get this instead. And this we can evaluate. This our calculator can do. So the change of base formula will allow us to solve logarithms that we otherwise wouldn't be able to. Having said that, back in the day, long before I was in school, it used to be that mathematicians would have these libraries of books that were just logarithm tables. And it would be like log base 10 of a bunch of numbers, or log base e of a bunch of numbers. And these would run over hundreds of values. And that's how they would calculate things. They would use these log tables and say, all right, that with the change of base formula, let's figure out what this thing is. If I wanted log base 3, I'd go to my change of base formula in my book of logarithms and figure it out from that. Now we have the problem of our calculator is restricted to just 2 logs. How are we going to work that out? And that's why the change of base formula is useful and important. It also gives us a way of evaluating the derivative of these things. Notice, when I talked about the derivative of a logarithm, I talked about it in terms of the ln, not of a general base. Now, we have a way of rewriting a logarithm as the ln. It can solve the derivative of a general logarithm, right? Everybody cool with this? So having said that, just as a couple quick examples, log base 2 of 3. If we wanted to rewrite this and solve using the change of base formula, say log base 2 of 3 is equal to the ln of 3 divided by the ln of 2. I want to point out this one can't be solved because -1's not in the domain, right? It doesn't matter what your base is. There's nothing, no real number that you can put in as a power and get a negative out, right? Make sense? So just to see that a little bit more clearly, log base 2 of -1 is asking us to solve this problem. But there is no y that we can raise 2 to get -1. So C here has no answer. So it's not enough just to look at these. We have to start thinking more critically about what we're passing through the logarithm as well. Having said that, just really quickly want to point out, log base 2, -1 is not defined. Log base 2 of 3 is the ln of 3 over the ln of 2. That's what we've got. Since we are 5 minutes over, I will let you all go.